All right, hello, my lovely students. So, finishing out our lecture on section 4.5, the shape of the graph. So, we were looking at this very crazy derivative, and plugging in numbers there is definitely much easier with the help of a calculator. But I have over here the Desmos graph. So, we can see here if this is -2, this halfway mark here is -1. To the left of -1, this is the graph of the derivative, well, part of the derivative. Um, no, that's the whole thing, but yeah. So it's negative before -1, positive after -1. And then when we look over here at 3, in between 0 and 3, it's negative. After 3, it's positive. So I could pick test values in there, but I mean, like literally, I just click on the graph. When I plug in 3.25, it's a positive number. And now I move down here, plugging in almost 2. I'm getting negatives. And then in here, positives. So just another way of seeing where those values are without having to actually like crunch them. So finishing our first derivative test. Okay. So what we have is the graph is decreasing. And then it's increasing. And then it's decreasing. And then it's increasing. So from our test values, we're seeing a local minimum, then a local max, then a local min. So answering our question, find all local extrema and determine when the graph is increasing and decreasing. So we have a local min at -1 and at 3. And we have a local max at x equals 0. All right, now we're going to answer the increasing and decreasing part. So the increasing is from -1 to 0. And my brain is like, and then you stick it together with a U, except our WebWork says, no, I hate U's, I want a comma. So sometimes it'll take the U, but sometimes it gets real pissy. So we'll put a comma. And then it's increasing again from 3 and everything after, so that's up to infinity. Now note, these are all parentheses. At the points themselves, the slope is 0, so it is neither increasing nor decreasing, or the slope is undefined. All right, then it's decreasing from -infinity to -1, and from 0 to 3. Now, if you were curious what this 0, because it was a critical number, but it was a critical number because it was undefined in the derivative. And on a graph of the derivative, it's an asymptote. Like if I zoom out here, you can see, yeah, that's asymptotal behavior. All right, this other graph I have here is the actual graph itself. This is the function we were looking at. So let me take the derivative off for a second. So you can see we got a local min. The graph comes to a funky sharp point, and then there's another local min. So this sharp point still right around there is a maximum. It does go increasing to decreasing, just does it a little weird. If you study a lot of polynomials, the fractional exponents, x to the 1/3 versus x to the 2/3, will demonstrate this kind of behavior. It's the whenever the numerator is squared, you'll get these kind of wonky points. like here, x to the 2/3. See? Corner point. Now we can even compare the 0 on the red graph corresponds to the min on the blue graph. The wonky critical value from it being undefined is actually corresponding to the wonky corner point. And then our other min occurs at 3. It's a little off the screen, but that's when the red graph is 0 and goes from negative to positive, decreasing to increasing. So it was a lot harder to see these graphs back in my day, but it's nice to be able to see the two together, and then I find a little easier to kind of correlate that. A 0 here is a flat point. A 0 here, another flat point down there. All right. So we have answered the question. Now let's see what craziness we have with the second derivative test. And let me put some space in here, because we all know I'm going to write too big. Find all inflection points and determine when the graph is concave up and concave down. So this is asking us to play around with the second derivative. Now looking at this, we've got a product rule. We could pull the x into the square root and just do it with a chain rule, but sometimes that's useful. A lot of times it's just a mess. And doing a chain rule, we're still going to get times other stuff, so we may as well just work with the product rule. So f prime of x, my first thing is x versus my square root. All right, so I'm going to keep the x, and I'm going to process that is x squared plus 7 to the 1/2. So I focus on my outside derivative. The 1/2 comes down, ugly, to the negative 1/2, because that's 1/2 minus 1, and then times the derivative of ugly. So let's go ahead and fill in ugly, x squared plus 7, and then the derivative of ugly, x squared plus 7 there, is 2x. Plus, that was only half of our derivative. So that was keeping the x, doing the derivative of the square root. Now we're going to keep the square root, do the derivative of x, which is boring 1. So we have 1 times x squared plus 7 to the 1/2. All right. Now I'm seeing that x squared plus 7 to the 1/2 like showing up in both terms. In one term, though, it's on the bottom. And then the other one, it's on the top. So maybe we could factor it, but I don't know. What I can say for sure, though, is I've got the x, the 1/2, and the times the 2x. I need to clean this up before I do another derivative. So the 1/2 times 2 actually cancels out. So I've got an x times an x. So x squared times x squared plus 7 to the negative 1/2 plus x squared plus 7 to the positive 1/2. All right, now we'll take a look at our second derivative. So again, we have another product rule. So I'm going to keep x squared and do the derivative of this craziness. So that brings a negative 1/2 down. Times ugly, negative 1/2 minus 1 is now negative 3/2. And then again, our derivative of ugly is still 2x plus 2x times our x squared plus 7 to the negative 1/2. That completes the product rule of the first part. Plus, now we can do the derivative of the just square root part. So we bring the power down, 1/2 x squared plus 7 to the negative 1/2 times the derivative of the inside is again 2x. So it looks like, oh, we got a 2x everywhere. The computer is driving me bonkers. All right, well, let's do a little bit of cleanup. See what kind of common terms we have. All right, so it looks like this front one is going to be a negative, but the 2 and the 1/2 will cancel. So I have -1 x³ times my ugly x² plus 7 to the -3/2. Then, so strangely enough, I'll just go ahead and write it because it really is strange. So that's 2x times ugly to the -1/2 plus x times ugly to the -1/2. So those, strangely enough, are like terms. So I have 2 crazy ugly plus 1 same crazy, same ugly. So I can count those together. 3 crazy ugly. 3x times x² plus 7 to the -1/2. All right. So we are supposed to set this equal to 0 and see what we can see. So dealing with fractional exponents is complicated. So I've got ugly to the -3/2 and ugly to the -1/2. All right. I'm going to factor out ugly to the -1/2. We'll put a little star there and write the rest. So when I multiply this back, the powers would add. So it would be -1/2 plus -1. That still gives me a fraction that I just don't want to deal with. So magic of computer, I'm actually going to change this to factoring out the ugly to the -3/2. So now the -1x³, its ugly is the one that we pulled out, plus 3x times. So I'm asking myself, -3/2 plus what number adds back to -1/2? If I add one positive whole, -3/2 plus 1 is -1/2. Okay, so now I have an ugly, disgusting mix that I cannot let be 0. And then I have something that's at least more polynomial-like. All right, so I have x² plus 7 to the -3/2 equals 0, or this will be 3x³ minus 1x³ will be 2x³ plus 21x equals 0. So this guy over here, if I raise both sides to the -2/3, it like, the fact that it's negative is actually like a negative power is problematic. So this is really 1 over x² plus 7 to the +2/3. But what it basically means is like when we have a thing to a power, whether that power is positive or negative, when we're doing our first and second derivative tests, the critical values are whatever would make the inside zero. Because either it'll be zero or it'll be 1 over zero, which is undefined, but both of those are critical values. So really, I'm just asking, when is x squared plus 7 equal to zero? Well, now it's like, oh, wait, I can minus the 7. And I have x squared equals negative 7. Oh, that don't happen. All right, so that didn't give us any critical numbers. That's what that result means for us. So we ignore it. Cool. So now we got this 2x cubed plus 21x. I'm going to factor out the x. That will leave 2x squared plus 21. So x equals 0 is a critical number. It is very often a critical number. And 2x squared plus 21 equals 0. And if I start to try to solve this, I minus the 21. And it's like, oh, 2x squared equals negative? Nope. Not going to get any real numbers out of that. So we only have one critical value. So now we have to see if x equals 0 is an inflection point. So we got our number line. There's our 0. So I want to plug in -1 and I want to plug in +1. The good news is, like, plugging these in isn't too bad. But we got to plug them into our second derivative. So we're going to test those in this. -1 squared is positive, plus 7 is positive, raised to a power is positive. -1 cubed is negative, times the -1 outside, positive. Over here, the x squared plus 7 to a power, that's all positive, times a negative. Now it gets more interesting. Now I gotta wonder if I can convince power times -1 squared plus 7 raised to the -1.5. Maybe it'll take that. Okay, it does. And then plus 3 times -1 times -1 times -1 squared plus 7 raised to the -0.5. All right, it's negative. And now I'm going to copy that whole mess. I'm going to paste it again and back where the x's were. So that -1 in front stays, but inside here, I change that to a +1. Change that to a +1. And then it was 3x, so that becomes positive. And that becomes positive. Let me get positive 1.0165. Okay. So on our derivative, we tested -1. We got negative. We tested +1. We got positive. So this is concave down to concave up. So x equals 0 is indeed an inflection point of this disgusting graph. So that's our first part of the answer. Find the inflection point. There's an inflection point at x equals 0. And then determine concave up versus concave down. All right. Concave down is to the left of 0, so that starts at -infinity up until 0. And then concave up will go from 0 to infinity. All right. That is still a horrible graph. And then the last one. So I want the local extrema and the inflection points, and then a sketch of the graph. All right. So looking at our original function, like first look, it's like, oh, this is rational. Are we going to have asymptotes? So we've got like our first, can 1 plus x squared equal 0? I'd minus the 1 over, oh, no. All right, no vertical asymptotes, cool. Remember, vertical asymptotes occur when the graph would be undefined, which is when the bottom would be 0. All right. So there's not much we can do with this outside of the quotient rule. Technically, the bottom is a quadratic, the top is a quadratic. We could do polynomial long division, but most people find that more painful than just doing a quotient rule, so we'll do a quotient rule. Give you guys some good practice anyway. So here's our low, here's our high. F prime of x. Low, 1 plus x squared. D high, 16x plus 2, minus high, the whole crazy 8x squared plus 2x plus 8. D low is 2x. Square the denominator. And away we go. All right. Now, since this asked about inflection points, we're going to have to do the second derivative. To do the second derivative, like for the stuff on the bottom, we could multiply it out. We can also just use chain rule when we have to do that. But on top, it'd be better to clean that up, multiply it out. So it's going to be ugly, but we can do it. All right, so when I multiply 1 times 16x, that'll be 16x plus 2 plus 16x cubed plus 2x squared. And what I'm hoping is maybe we'll get some cancellation. So minus 16x cubed, haha! And then the minus 2x times 2x minus 4x squared. All right, not full, but that's okay. And then 8 times 2x, 16x, but with the minus 16x. I'll take it. That's still quite a number of them gone. All right, so just going to use my orange here. 16x minus 16x minus 16x cubed with positive 16x cubed. All right. So I got 2x squared minus 4x squared. So I'm going to go ahead and write that 2 first. So it is 2 minus 2x squared over 1 plus x squared squared. So doing our first derivative test, we have to find critical values. So critical values are when the top of the fraction is 0 or when the bottom of the fraction is 0. If a number shows up in both lists, cool, it's still a critical value. But it means when we're like finding the critical values, we're not trying to do it to the fraction, we just split it. So I got 2 minus 2x squared equals 0, which that'll give me 1 equals x squared. So we get plus or minus 1. All right, so we get two critical values there. Nice. And then the 1 plus x squared, I minus the 1 and then try to square root. No, this doesn't happen. Which we learned earlier because that's what we checked for vertical asymptotes. All right, so our only critical values are positive and negative 1. So our number line for our first derivative test. There's our negative 1, there's our positive 1. Oh, okay. So our formula in orange over here, that's not too bad to work with. So let's put in -2, see what happens. -2 squared is +4 times -2 is -8. 2 minus 8 is -6. All right, so this is -6 over -2 squared 4 plus 1, 5 squared 25. All right, so we got negative all through there. Now I'm going to test 0. I know it looks like I just wrote a donut. So 2 minus 0 over 1 plus 0, it's positive because we just get 2 over 1. Now coming over here, we're going to test out 2. So 2 squared is 4 times the -2 minus 8. 2 minus 8 is -6 again. And we're going to get the 25 on the bottom again. All right. So our first derivative test results are telling us decreasing to increasing to decreasing. So our verbal part of the answer here, we have a local min at x equals -1 and a local max at x equals +1. All right, now the second derivative test. All right. So this is going to be another quotient rule. Now I will say this. We are doing these now on the videos because there might be one of these on the web work, but also so we don't put it on a test. Asking you to do this for like a polynomial can be a little long, but that's reasonable on a test. Or more giving you the first derivative, asking for the second, asking you to do the first and second derivative tests, and then give me a rough sketch. Very reasonable. All right, so low is 1 plus x squared squared times d high, high. So the 2 at the front is just a number term, it goes away. So -2 times 2 is -4x. So low d high minus high 2 minus 2x squared d low. So the bottom now, the 2 comes down, 2 times 1 plus x squared to the first times the derivative of the inside, 2x. So chain rule going on there, but we got it. Square the denominator, so that's 1 plus x squared squared squared, which the outer two 2's multiply and become a 4. All right. All right. So at the very least on top, there's at least the 1 plus x squared in both of them. I also see an x in both of them. And I could even like pull out 2 times 2 or pull out a 4. All right, so they got quite a bit in common. So I said a 1 plus x squared was in common. There's also an x and a 4. So here, that'll leave me with 1 plus x squared, but it's not squared now, it's just the single, times the 4 and the x are out, so I just need a minus, and I put a 1 as a placeholder. Because if I distributed back, 4x times the negative 1 would be the negative 4x. Minus. So that 2 minus 2x squared, like I didn't put any highlights there, so we're just going to keep it. But everybody else there is actually up front. 2 times 2x is 4x, 1 plus x squared, 1 plus x squared. Over 1 plus x squared to the 4th. Our second derivative. All right. Now, one of the nice things here, the 1 plus x squared does cancel out one of the 1 plus x squareds on the bottom. So that leaves us with 3 of them. So now I'm just going to go ahead and take the time because we're going to want to simplify it a little for the solving when we set it equal to 0. So that is now 4x on the outside, negative 1 minus x squared minus 2 plus 2x squared. All over 1 plus x squared, whole thing cubed. All right. So that's going to be a positive x squared minus 3. I am lazy. All right. We got a lot more critical values the second time around. So the good news is the bottom never equals 0 because it's the same bottom we've been dealing with. That 1 plus x squared never goes negative, never goes to 0. All right. So on top, we're going to set that equal to 0. Now we'll actually get some stuff. I've got 4x equals 0, or you could write it 4 equals 0, x equals 0. And then our other one is the x squared minus 3 equals 0. So the 4 equals 0 never happens, or you leave it as 4x, divide by 4, you get x equals 0. And then over here, we'll have x squared equals 3, and then we square root. So we have plus or minus the square root of 3. All right. Well, let's put together our second derivative. Got a lot more going on. Negative square root of 3, 0, positive square root of 3. Make that line a little longer so I see 1, 2, 3, 4 regions. All right, so negative square root of 3 is like negative 1.7. So I can pick negative 2 as the test value, negative 1, positive 1, and positive 2. And just to speed things up, I'm just going to calculate on here. So you guys will see how I'm typing it if you want. I need to go back and put the times. Times. Open and open another. Negative 2, close squared. And then the minus 3. Close that. You can put a whole nother set around the top if you want, but since all the outer operations are multiplication, I am okay to just put divided by. I am going to put 2 parentheses here though, just because it might make a difference. So negative 2 squared, and then we're raising that to the third power. So I see 1, 2, 3 spots for the x's. All right. So it tells me -2 is negative. So there's that. All right, now we're going to go and change those 3 -2's to -1's. Come over here, equals. Oh, look, it actually worked out nicely. All right, now I'm going to come back in here and put in +1, which I bet we'll get like 1 or -1. -1. What you're going to see in a lot of these is typically it alternates as you're doing the regions. Not always, but very often, especially if there was no vertical asymptotes. Around either side of an asymptote, they're usually the same because it's usually like down and up. All right. And now we're just going to take out the minuses. So we should get that answer we got first, but positive. Indeed. All right, now this is our second derivative test. So this does mean we have 3 inflection points because the concavity is changing on all of them. So we have inflection points at x equals -√3, x equals 0, and x equals +√3. Now, let me come back over here. I want to label which one was which before we get too far from it. All right, so my first derivative test, I had -1 and 1 as critical values. The second derivative test has a lot more, -√3, 0, and √3. The good news is I don't have to pick any more test numbers, but I do have to compile the information together into like one giant number line. So actually, while I'm thinking about it, let me zoom back in here. Concave down, concave up, concave down, concave up. I'm going to take a screenshot of my second derivative test. Come on, computer, I believe in you. All right, so there's that. And now I'm going to screenshot the first derivative test. Let's go ahead and shrink that a little. And now we are going to make one giant large number line. All my critical values from both of them are going to go on this number line. So -√3, -1, 0, 1, and +√3. All right, so our first derivative said everything before -1 is decreasing. And then our second derivatives told us some information about the concavity there. All right, so decreasing with negative concavity. Yeah, let me grab a different color. So a downward arrow, but it can't hold oatmeal. And then after -√3, our concavity goes positive, but we're still before -1, so we're still decreasing. So we go from the not holding to, oh, now it can hold a little. Sorry, let me make that a little prettier. Now, from -1 to 0. So between -1 and 1, I'm increasing. So on both of these two, I'm increasing. Between -1 and 0, my concavity is positive. So now I'm going up with positive concavity. And then after 0, my concavity is negative, but I'm still increasing. And now after 1, I'm decreasing again, and I'm going to have the flip-flop with concavity. So a decreasing negative concavity, and then a decreasing positive concavity. So, absolute madness. So now what I'm going to do is I've got my X labels. I need tick marks on the X-axis because I have to correlate my critical values to the X-axis. What I do not need is Y values. So I've got the Y-axis marked because it's establishing where the 0 is. But other than that, I'm not going to put any tick marks on it because this graph could be all sorts of different stretches, but the overall shape so our negative square root of 3 is going to be around here. So it's going to be like decreasing, still decreasing. And then at -1, we have that min. So now we're going to get the increasing until we get to 0 with positive concavity. And now from 0 to 1, we get that curve. From 1 to around the square root of 3, we get that curve. And then from square root of 3 on, we get that curve. Now the endpoints probably don't actually point like straight left and right. They're, probably a little more angled up and down, but that is our overall rough shape of the graph. So the inflection point does occur on the y-axis. I have no clue where on the y-axis. I could figure that out, but generally when we're doing curve sketching, we're not so interested in what the actual graph does, so much as placing the inflection points and the maxes and mins. But I'll admit, I'm curious. I want to know. So tell me, Desmos. Give me the big fraction. 8x squared plus 2x plus 8 over 1 plus x squared. Oh, I guess it did flatten out, huh? But I zoom it in, and this is -2, so our inflection point is happening somewhere around here, like literally. And then our other one is happening somewhere around here. It's harder to see because the graph is a lot more stretched out, but you can see a little bit of the, like, not holding oatmeal to, a slight, yeah, it'll hold some oatmeal on this side. So our particular sketch was a lot more extreme on our curves, but it still matches that overall shape. All right, so that is like all the nitty gritty and then a final put it all together, everything all at once. First and second derivative test, compile it together, get our little curvy lines and do a rough sketch. All right.